about an introduction to calculus in the sense of the concept of rate of change. We have discussed about the concept of rate of change in context of average speed versus instantaneous speed, being the average rate of change versus the instantaneous rate of change of distance with respect to time. So today we will carry that discussion forward and understand the more general definition of instantaneous rate of change in the context of calculus, or the calculus definition of it. Okay. So this is our second session of basic calculus. Now, this is basic calculus over here because we will be studying a more advanced version of calculus as part of our math syllabus in class 12. But here we will be studying the essential fundamentals of calculus, which are going to be utilized in our study of physics throughout class 11th as well as 12th, and in future in physics. So it's more like an introduction and fundamental aspects of calculus, which are for the purpose of application in physics. Okay, so calculus on its own is a very interesting and also a more complex subject, but certain fundamentals of it are essential before we start our study of physics. And by understanding those fundamentals, okay, we unlock a lot of principles in physics, which is going to make things more intuitive and more easy to understand as we go along. Okay, so let's start with that. So I think few students have just joined in. Anyhow, so with everybody present more or less now, let us begin. So yeah, as I was saying, that just to recap what we have done in the previous lecture. So we were talking about instantaneous speed versus average speed. So we had seen that average speed is the what we call the average rate of distance covered with respect to time. Or in more everyday language, you might just say distance traveled divided by time taken. Okay, so we had seen the formula for average speed becomes total distance in a certain interval of time divided by the time interval. So that we might say is S2 minus S1 divided by T2 minus T1. We are thinking in terms of the graphical context, or in terms of a direct formula. Okay. So the important thing is that average speed is defined for an interval of time from T1 to T2. So it is defined for a specific time interval. Whereas when we discussed about instantaneous speed, we saw that it's a somewhat more confusing and more abstract concept. So we saw that instantaneous speed is the speed at an instant. It means that at a particular moment of time, or at a particular instant of time, what is the rate of distance with respect to time? Okay, but that is for an extremely short interval. That's what we mean by speed at an instant, that instantaneous speed becomes like a delta S by delta T, but with an additional qualifier that delta T is extremely short. This is the sort of intuitive definition of instantaneous speed that we were talking about last time, because instantaneous speed is defined at an instant, not for an interval. So we had seen, for example, that if we talk about instantaneous speed versus average speed in terms of how it is measured, okay, because after all, physics is a subject dealing with physical quantities, so measurement is an extremely important part of physics, and how we measure and calculate quantities using measured values is extremely important to understand. So when we talk about the measurement of instantaneous speed, for example, a speedometer or a speed gun, infrared sensors, etc., how they measure is that they calculate the distance traveled for a very, very short interval of time. So for example, if a particular instrument is measuring instantaneous speed for a millisecond, we can say it's reasonably accurate. But if we have an infrared sensor which is measuring speed, for example, for a microsecond instead of for a millisecond, it's able to calculate the distance covered in 1 microsecond as opposed to 1 millisecond, and then calculate the instantaneous speed using that. Then the infrared sensor using the value of delta T as a microsecond is much, much more accurate compared to, let's say, a normal speed gun, which would measure it for a millisecond. So basically, in short, what we are saying is that the smaller the value of delta T, the extremely short time interval for which we are measuring distance, the smaller the value of that delta T, the more accurate we can say our measurement of instantaneous speed is going to be. Whereas average speed is measured in a different way. Average speed is measured for a certain time interval, which is comparatively larger. Okay, so we measure the total distance covered in that entire time interval from T1 to T2 and divide that total distance by the time interval. So that in general was average speed and instantaneous speed. So we will today take this discussion forward, and we will see how instantaneous speed, or in a more general sense, the instantaneous rate of change of one quantity with respect to another is defined in terms of the calculus definition, and how the subject of differential calculus, okay, gives us a method, a set of formulae, a systematic approach to calculating instantaneous rate of change. Okay. And again, talking in context of the general definition of instantaneous rate of change, it might be for any physical quantity with respect to another. It's not limited to just speed as distance versus time, or velocity as displacement versus time. We can talk about the instantaneous rate of, for example, change of momentum with respect to time, which will relate with force. Or we can talk about instantaneous rate at which charge is flowing with respect to time, which will be instantaneous current. Okay, and many other such definitions in future. So we have to develop a more general approach towards the rate of change of one quantity with respect to another. Okay, so that brings us to that brings us to, as I said, the calculus definition of instantaneous rate of change. So we will begin our study of basic calculus by studying about what is called functions, okay, because calculus applies to functions. And through that, we will study rate of change in more detail, which will be about differential calculus. So what we'll understand is that calculus has two parts, and the first is differential calculus, which has to do with the concept of rate of change. So let's begin by understanding what is a function. Can anybody define the term function for me in context of maths or calculus, not in context of the everyday meaning of the term function?
Relation between variables.
Yes, very good. That's correct.
So relation between an independent and a dependent variable.
Yeah, very good, Vinny. That's a very good definition.
in the form of y is equals to fx.
Yes, it is written generally in that the general notation is that y is a function of x or y is equal to fx. Very true.
A
Okay.
certain operation that takes certain inputs and gives certain output.
Yes, Darsh, can you speak a little bit louder, beta? An operation
It
that
is a certain mathematical operation that we can define, so it can take certain input or inputs and give outputs based on that.
okay, so it's a certain mathematical operation, okay, where if we input a certain value of a variable, then we get an output of another variable. Is that correct?
Yes.
Okay, very good. Can anybody give me an example of a function or two, like
Trigonometric function, square function.
yes, very good. So
exponential functions.
So give me an example of a trigonometric function, like in terms of y and x.
Y is equal to sin x.
Y is equal to sin x is the most basic of the trigonometric functions, right? But for example, we can also have y is equal to sin square x. That's another trigonometric function, right?
Yes, sir.
Okay, very good. So let's write down the definition of a function. Okay, the way like you all have described correctly. So function is a relationship, you can say, a relation, or we can say it's a maths expression, okay, that defines the value of what we call a dependent variable. And generally we denote that dependent variable with the symbol y, okay, for, or you can say in terms of the value of an independent variable. X. So it's more or less what we have all just been talking about, that it's a relationship or a expression that defines the connection between two variables x and y. So the mathematical symbol for it is that y is equal to, so this complicated line that we've written on top, it can be just simplified into one single formula or one single expression, that y is equal to fx. This statement here means that y is a function of x. Okay. And by convention, when we write something like this, whatever is on the left hand side, in this case it's y, that is the dependent variable. And whatever is on the right hand side, the expression is of a variable which becomes what we call the independent variable. So why we are calling these dependent and independent variable means the value of x can be chosen independent of the value of y. Okay. The value of x can be chosen or selected independently without any consideration to what is the value of y. Okay. Whereas the value of y is dependent on the corresponding value of x. So for a given value of x, corresponding value, okay, so it's dependent on what value of x we have selected. So that's why it is called the dependent variable. Okay. Now you might say that, okay, if we select some value of y, then we can use the formula of the function to calculate the value of x also. So then why is x not the dependent variable? So I will say that yes, that's true, but it's a matter of convention. When we write the function in this form, whatever we write on the left hand side, we mean to suggest that that quantity is the dependent one, whereas whatever expression we write on the right hand side, that expression is of the variable which is the independent one. So it's a matter of convention. It's how we define the function. Okay. Now obviously the symbols are y and x are the standard symbols, but when we apply functions in physics, these symbols are going to change. So for example, we can have a situation where distance is a function of time, or displacement is a function of time, or velocity is a function of time, or we can have something where velocity is a function of displacement. So all these different symbols. Okay, so for example, here this t could be time and s could be displacement. So in this case, we will say that displacement is being expressed as a function of time. And an example of that is that s is equal to half at square. So here a is a constant, t is an independent variable, and s becomes dependent on the amount of time. At 1 second, the distance covered is a certain value. At 2 seconds, the displacement or distance is another value, like that. So that's an example of a practical application of a function. Okay. So hope things are clear so far. If there's any doubt, please let me know. Okay. So let's look at some examples of functions. So for example, one of the easiest instances to understand about function is a linear function. Y is equal to, let's take some simple straight line equation. Y is equal to 2x plus 3. This is an example of what we call a linear function. Okay. Let's say y is equal to 3x square plus 5x plus 2. This is an example of what we call a quadratic function. Both linear and quadratic functions are particular members of a certain family of functions, which we call polynomials. These are examples of polynomial functions. Okay. The general expression for a polynomial function is a power series, some constant plus some constant into x plus some other constant into x square plus some other constant into x cube, and can go up to any power. So this is the general polynomial of, we say, degree n. Okay. So when that n is equal to 1, we are talking about a linear function. When that n is equal to 2, we are talking about a quadratic function. If n is equal to 3, we call that type of function a cubic function, and so on and so forth, right? Here a0, a1, a2, a3, etc. These are constants. Okay. So there are only two variables we are talking about, x and y. And because we've written y on the left hand side, y is the dependent variable and x is in the expression on the right hand side. So x is the independent variable. Okay. Of course, the question might occur to you that why we are limiting ourselves to two variables. A quantity can depend on more than one independent variable, and that's very true. So functions are not limited to single variable functions or single independent variable. There is a case where we might define a function of multiple variables. For example, the temperature inside a room might depend on the location of the point we're talking about and the amount of time. So temperature can be a function of the XYZ coordinate as well as time. So it might be a function of 4 variables. Okay. But that is going to become more complicated and going to go a little bit outside the scope of our level of mathematics here. So for the moment, at your 10+2 level, when we talk about functions, we are talking about functions of single independent variable. So one dependent variable defined in terms of a single independent variable. That is our understanding of functions so far. Okay. More examples, we are talking about trigonometric functions just a minute ago. So y is equal to sine x is an example of a trigonometric function. Y equal to, let's say, tan square x, or y equal to tan x. So all these are examples of trigonometric functions. They are in the category of trigonometric functions. Whereas when we talk about sine x, we will specifically say, it's the sinusoidal function or the sine function in short. Okay. So there's a lot of terminology as we go along, but don't get confused with all that. Okay. Then exponential function is another example, e raised power x. Can anybody tell me what this symbol is? Y is equal to ln x. What does it stand for?
Natural log.
Natural log. Very good. So what is natural log?
Log to the base e.
Log to the base e, right? How it is different from standard log? Standard log is to the base
10.
10.
Okay, whereas natural log is to the base e. Very good. So this is what we call the logarithmic function, so on and so forth. Okay. All right. Now, another way to interpret a function, okay, or to understand a function is what we call by the geometrical interpretation, or that is through graph. Okay. So a graph of a function it is a way to geometrically interpret a function. So I'm sure all of you know what is a graph of a function, but just to reiterate, when we represent a function y is equal to fx through a graph, we have to follow a standard convention that the dependent variable must be on the horizontal axis. Okay. It's very important. And the independent variable must be on the vertical axis. We should not interchange these two, because otherwise things like rate of change will become inverted in their meaning. Okay. So we must take the vertical axis as what we have on the left hand side, the dependent variable. And the horizontal axis must be used for the independent variable. And then what we can see is that for a given function, let's say y is equal to fx, a crude way to understand the graph is that we can generate some values. X1 has a corresponding value y1 equal to f of x1. X2 has a corresponding value y2, is f of x2. So like that we can define a set of ordered pairs and plot these points on the two-dimensional graph or on the two-dimensional space. So if these points, for example, represent x1, y1, x2, y2, and so on and so forth, then an extremely basic way of drawing the graph would be to to generate a certain number of points using the formula of the function like this. So for that, we can just select appropriate values of x1, x2, x3 like this. And after having plotted these points, do a sort of guesswork, okay, that in between these, the function is represented by the smoothest possible curve. So this is the crude and very basic way of drawing a graph. Okay. A more accurate way of drawing a graph, for example, would be to write a computer program, okay, which will select literally infinite number of points. Okay. So for example, it might take x1 as 0. It might take x2 as this much. It might take x3. So it will do something that we cannot do by hand because it is too tedious and too lengthy. But because a computer algorithm can run, in virtually infinite times through a loop. Okay. So it is possible that it can generate a very, very large number of points. And when it plots that on the screen, so when we plot the points, they are so close to each other, all these points, that in continuation, they become the curve itself of the function. Okay, so then that becomes a more accurate way of drawing the graph. Okay, of course, our focus here will not be on the accuracy of the drawing of the graph. Our focus will be on understanding the properties of the function from the graph itself. So it will be about drawing approximate graphs. But having said that, what is the definition of the graph of a function? Okay. So the most accurate definition would be that it is nothing but a continuation of points such that each of those points is satisfying this given relation. So on the two-dimensional plane, the graph of a function is a curve So it is a curve such that all points on it satisfy the relation y is equal to fx. So each and every point on this two-dimensional plane that satisfies this particular relation the collection of each and every such point together becomes what we call the graph of the function.
So can it be a straight line?
Yes, the graph can be a straight line. In fact, in the case of linear function, it is a straight line. Okay. So common examples of graphs, if we take. So examples of graphs of functions which are commonly used in physics. Okay, so in that, the first example we will take, in fact, is the linear function. So the general formula for linear function we will write just like the formula for a straight line, y is equal to mx plus c, where m and c are constants. So depending on the value of m and c, the straight line can have a positive slope or a negative slope, can have a positive y-intercept or a negative y-intercept. All these different possibilities are there. So let's take some examples. So for example, if I have y is equal to 2x plus 1. So this will look like a straight line which has a positive slope and a positive y-intercept. So this has m, which is plus 2, and it has y-intercept, which is plus 1. So this point where it crosses the y-axis, this point will have a y-coordinate of 1, or precisely its coordinates of this point will be 0, 1. And also, if I select any 2 points, x1 and x2, and calculate the average rate of change between these 2 points, that is the change in y upon change in x, I will see that that ratio will be equal to how much? That ratio will be m, which in this case is 2. So we will see that tan theta equals to y2 minus y1 upon x2 minus x1 for any 2 points will be equal to the slope, which is 2. That is this type of line, which has a positive slope and a positive y-intercept. Now, similarly, if we have a line, let's say y is equal to 3 minus x. Now, this one is having a slope which is negative, but a y-intercept which is positive. So this will have a shape which is basically something like this. So this will be cutting the y-axis at a point which is positive, but it has a slope which is negative. So here, if we calculate the value of y2 minus y1 upon x2 minus x1, it will give us a negative quantity, which also means that the angle it is making with the x-axis, the positive x-axis is this one, which is an obtuse angle. So m being negative means that tan theta is negative, which means that theta will be obtuse. Okay. You must have done this in trigonometry till now. How do we calculate tan of an obtuse angle? If theta is between 90 and 180, how do we calculate tan theta? Can you tell me the value of tan 150 degrees? Anyone?
Minus tan 30. So minus 1 by root 3.
Minus 1 by root 3. Very good. Tan 150. So how we calculate it? We write it as tan of, let's say, for example, we can, one way to express it is that it's 180 minus 30. So it becomes minus of tan 30. So it becomes minus of 1 by root 3. Or you can also express it as 90 plus 60. So for example, this is an important little formula. So anyway, so here what happens is that you can see that y2 minus y1 upon x2 minus x1, which is equal to tan theta, is going to be a negative quantity, and that's going to be equal to the slope in this case, which is minus 1. So in this case, the slope is minus 1, will indicate that theta is 180 minus 45 degrees. So it's inclined to the x-axis, the positive x-axis, making an angle of 135 degrees. Okay. Whereas this particular line, if we talk about the angle, so tan theta is equal to 2, means theta is what we call tan inverse of 2. So that's not a standard value, but you will see that it's close to about tan inverse 2 will be close to about will be close to 52 degrees or something like that. Okay. I can use calculator to give you the exact value. Yeah, so if we use a scientific calculator to calculate the tan inverse of 2, so it's about 63 degrees. It's approximately 63.4 degrees. Obviously, because we know that tan 60 is root 3. It's 1.732 approximately. It will be slightly greater than 60. So it is about 63.4. So anyhow, the value is not so important right now. What is important is that in terms of rate of change, we have two types of linear functions with positive slope and with negative slope. And this is how their graphs look. Now, of course, the y-intercept also becomes important. So for example, if we have a graph like this for a straight line, this is one which is having m positive but y-intercept negative, because where it's cutting the x-axis, the y-axis, it has a negative value of c. Okay, or we can have a graph like this one of a straight line where both quantities are negative. M is also negative, the y-intercept is also negative. Okay, so this is in general how the graph of straight line looks like. Okay. Now, before we move ahead with more graphs, okay, there is one point I want to make about functions. Suppose I have a function like that, y is equal to square root of 1 plus x square. And I have another expression which I've written as y square is equal to 1 plus x square. Okay. So the question here is, are these two expressions equivalent?
No, sir.
No, sir.
No, they are not equivalent. Okay. Are they functions?
Yes, sir.
Yes, sir.
Or okay, now why are they not equivalent? Can you tell me?
Because the value.
Only one value of y, but in the second one
There will be only one value, but in the
Yeah,
second
very good. So for example, if I take x equal to 0, so in the first equation, what is the corresponding value of y I'll get?
one.
Yeah, I'll get it as 1. But from equation 2, I'll get y square is equal to
Plus
1. That means y square is equal to 1 means y square minus 1 is equal to 0. So I'll have to simplify this further, right? So the proper solution of this one will be y is either plus 1 or y is minus 1. Right? So this is what all of you were saying. That's why they are not equivalent. Okay.
yes.
So you can see that. So that's true for any value of x. Okay. So for example, if we take x as, let's say we take x as 3. So from equation 1, we will get y as root 10. Okay, or approximately 3.2. But from equation 2, we will get y as root 10 or minus root 10. We'll get two values like this. Okay. So now, having said that, we'll understand that the second equation is not a function. Y square is equal to 1 plus x square is not a function. It is a relation, but not a function, because a function, now this is a very important thing, must define a unique value of y for any particular value of x. So when we take a function y is equal to fx, it must be able to define a unique value of y for every independent value of x. Okay, think about this. This is a very important statement because we are using functions to define physical parameters. Na? Like for example, displacement is a function of time. So at a particular instant of time, it is not logical that you can have two different displacements. Okay, it's only logical that displacement has one unique value at a particular instant of time. It might so happen that the displacement repeats after a certain time. So you can have two values of x which give you the same value of y, but you cannot have two values of y from the same value of x. Okay, so this is a very important property of a function. Okay, and if you're jotting down some basic notes, you can note this point down. Okay.
So can you explain that example once again?
Yeah, Alex. The example of the function earlier, or the y square is
Of
equal to 1 plus
displacement and time.
yeah, I'm coming to that. Okay, I'll explain that. Okay, so first let's note down this point. A function must be a relation such that for any particular value of x, okay, it defines a unique or a single value of y. Okay, so obviously we're talking about a function where y is the dependent variable and x is the independent variable. So if we interpret this statement graphically, now it means that I'm going to compare three different graphs. Okay. Now suppose my first graph is like this. My second graph is like this, but my third graph is like this. Okay, so this is a function. This is also a function, but this will not be a function. It's a relation, but it's not a function, because what is happening is here, see, for every value of x, you're having a unique value of y. Okay. So any x is giving us a single value of y. And so on and so forth. Okay, here also that's the case. For any value of x, there is a unique value of y. Yes, there might be multiple values of x that point to the same value of y. That's okay. Okay, so x1, x2. So in this case, the value of y2, the way I've written it, is getting repeated. But that's not the point. The important thing is when we look at a particular value of x, is giving us a particular value of y. But in this example, what is happening is that a particular value of x, let's say x1, is giving us three possible values of y. y1, y2, and y3. Now, this kind of relation is not allowed for the definition of a function. Okay, the allowed functions are only those relationships where a particular value of x points to a unique or a particular value of y. Okay, now the physical example I gave you is this, that imagine this is a distance versus time graph or a displacement versus time graph. So it might so happen that an object is, or a person is continuously moving in this direction only, so his displacement will only be increasing. Okay, it might so also happen that he goes like this and then comes back like this, so his displacement will first increase and then decrease and then maybe increase again later. So he could have a repeated displacement at two different instants of time. But is it possible that at a particular instant of time t1, the person is present here also and here also? This doesn't happen in normal physics, right? It might happen in the quantum mechanical world. Okay, but in classical physics, it doesn't happen that the value of displacement has two separate values at a particular instant of time. Are you understanding my example now?
Yes, sir.
But this graph is wrong. It means that
Which
the
one?
graph is wrong, right?
The third one,
Yes. The fourth one, the right side.
this one,
Yes, sir.
graph is wrong in the sense that
Because at the same time, a person cannot be at two places, right? So the graph is wrong.
in the fourth graph that's not happening. At a particular time, the value of displacement is particular only. See, it might repeat, but at a particular instant there are two. No? The wrong graph would be this, that this would not be possible, that at a particular instant of time, if the graph is looking like this, for example, then this is the wrong one, because this is showing you that at a particular instant of time, there are two possible values of S. This is not possible. This is the one that is not possible.
Yes.
This is the one which is happening when the displacement first increases and then decreases. You're understanding the difference, huh?
Yes, sir. So the third one is wrong.
Yeah, this one is wrong. This one is not a function. As you can see, this is not a function.
Sir,
Okay, it
so
can
why
represent the graph of a curve, of a relation, but it is not the graph of a function, because a function must be defined in such a way that a single value of x gives a single value of y. It does not give you multiple values of y. Is it clear?
Yes, sir.
Okay. So that is why, for example, if we were to plot the graph of, for example, if we are plotting y square is equal to x, then later in maths you will learn that this is what we call a parabolic graph. And this graph would look like this. So there's no problem with drawing this graph, but this graph now doesn't represent a function. This is the graph of a relation y square is equal to x, but this cannot be defined as a function.
Sir,
Yes,
sir, can we say that the x is the function of y?
but then yeah, that's a very good point here. But then according to convention, now what we'll have to do is we'll have to write it this way. If we invert this and say that okay, x is equal to y square, then yes, this is a function. Because
And
remember
still
what
be
is
with
our
the
convention?
y-axis.
It is a function.
The dependent variable is on the left hand side. So now we will say that x is a function of y. So this is okay. Okay, and the graph will look like this. And that's why it's always important that we must take the independent variable on the horizontal axis and the dependent variable on the vertical axis, so that we can check that every independent variable is giving us a unique value of the dependent variable. It should not give us multiple values. Here it's giving us a particular value of dependent variable x1 is giving us more than one value of y. So that's why it cannot be defined as a function. But if I had inverted this and written this as x equal to y square, then this is representing a function. This is representing a function of the type where x is the dependent variable and y is the independent variable. So I have to just interchange the axis.
Yes, sir.
Clear now this point? Okay.
Yes, sir.
Okay. Whereas if I had just taken the function y is equal to root x, then the graph would be different. The graph would be just one part of the curve y square is equal to x. That part of the curve that represents only positive values of y. So this is also parabola, but it's half this parabola. So this is representing y is equal to root x, which is a function. Or for that matter, I could even have the function y is equal to minus root x. This is also a function, and this one's graph would look like this. Okay. So this is about another important point about functions, that a function in general is a relationship between two variables, x and y, but with the restriction that the relationship must be such that for any value of x or the independent variable, the function defines a unique or single value of y. So that's the only restriction on the function. Okay.
So,
Now moving on. Yes, beta.
so can we say that every quadratic function is not a function but a relation?
Quadratic function, why beta? Because quadratic function is this type now. Y is equal to ax square plus bx plus c.
Because we generally tend to get two answers over here.
No, we don't get two answers, beta. See what happens. Let's take an example. See, you might be confusing quadratic function with quadratic equation. Okay, quadratic equation is a different thing. Like y is equal to, let's say I have whatever, let's say 2x square plus 3x, okay, plus 1, let's say. Okay, now this one, let's take some value of x. So for example, for x equal to 0, what value of y we are getting? We'll get a unique value of y, no? 1. For
Okay.
x equal to 1, we'll get a unique value of y, no? We'll get the value of y as 6. Okay. For x equal to minus 1, for example, we get a unique value of y. We'll get 2 minus 3 plus 1. So that's 0.
Understood. Thank you.
Understood? No? Okay. But for example, if I put y equal to 0, I'll get two values of x, no doubt. Okay. I'll get 2x plus 3x plus 1 is equal to 0. So the roots of this equation, as you know, alpha beta, they become that minus b plus minus root of b square minus 4ac. So in this case, minus 3 plus minus 1 by 4. So the roots will be minus half and minus 1. Okay. These will be the roots of the equation. Okay. So again, when we look at the graph of this function later in more detail, we will see that this graph is like this. It is having two roots. One of them is minus half and the other one is minus 1. So let's say they are like this. So it will be a parabola in between these two. Okay. Or you can say a parabola something like this, where this point where x is equal to 0, the value of y is becoming 1. So this point is 0, 1, as we have seen. Okay. But for example, by the time x becomes 1, the value of y jumps to 6. But any single value of x, we are having a unique value of y. But yeah, if we talk about this kind of relation, that y square is equal to 2x plus 1, let's say. So this is not a function because y is equal to plus minus of square root of 2x plus 1. So this is not a function. Don't worry about how we drew the graph of that particular quadratic function. Okay, I'll be discussing in a lot of detail about some tricks and techniques of drawing quadratic graphs. Okay, so coming back to graphs of some common functions. So let's look at the graph of y is equal to x square now. So this is a more interesting example of a graph compared to linear function that we're discussing earlier, because it has this kind of a shape. Okay. As you know, this kind of a shape is called a parabolic graph. So it has a situation such that for equal intervals of x, the change in y is not equal. It starts increasing rapidly. Whereas also y never becomes negative. For example, for 1 and minus 1, for 2 and minus 2, for 3 and minus 3, so on and so forth. Okay. So it has this interesting kind of shape which is called the parabolic curve, which is symmetric such that the y-axis is like an axis of symmetry. And the left-hand side of the y-axis, the negative x part of the domain is like a mirror image of the positive x part of the domain. Okay. Also, you will see that it has an interesting relationship with respect to a straight line graph. For example, if I just compare the graph of y is equal to x on the positive part of the domain with the graph of this parabola y is equal to x square, you'll see the interesting comparison that the line y equal to x exactly bisects this, okay, because it has a 45-degree angle or a slope of 1. Now, if you compare the parabola y is equal to x square to it, that will be a shape something like this. So you can see that up to the point x equal to 1, the line is having a larger value compared to the parabola. But at x equal to 1, y equal to 1, they intersect, and then the parabola has a larger value. Okay. Also, if you see, the parabola has what we call an increasing slope. The slope of the parabola is gradually increasing, whereas the line has a uniform slope. So if you draw tangents at different places, we were talking about tangents a little bit last time, you see that at every different point, the tangent has a different slope, whereas the straight line has a uniform slope. So tangent at any point is nothing but the straight line itself. Okay. Similarly, if you look at the graph of y equal to x cube, that also has an interesting shape. Sorry, I'll correct that to x cube. This has a shape something like this. It rises even more rapidly compared to the y is equal to x square graph. But on the negative side, it is an inverted mirror image. So they're symmetrical values. And so on and so forth. Okay. So trigonometric graphs we will explore in future. I'm not getting into them just now, but for example, the basic sinusoidal graph. One cycle of the sine graph, or you can say the sine curve, is like this. And then after 2 pi, it repeats itself because it's what is called a periodic or a cyclical function. So this is the graph of y is equal to sine x. You can say that it oscillates between the value of -1 and +1. As x goes from 0 to infinity, or even from minus infinity to plus infinity. If you compare the cos x graph to it, it's like exactly the same shape, but it is shifted. So there's a symmetry between the sine x graph and the cos x graph, which is why there's a symmetrical relation that sine of 90 plus x is equal to cos x, or sine of x plus pi by 2 is equal to cos x. So that symmetry you can see over here. Okay, so these are some of the common graphs. Exponential, logarithmic, all this we'll talk about. Okay. Another common one for you to consider is the hyperbolic graph. Y is equal to 1 by x. Now in this, one important thing is that at x equal to 0, what can we say about y?
Undefined.
Yes,
And
very good. Y
Not
is
defined.
undefined. Okay. But if I take y is equal to 1 by x, where x is tending to 0, but positive. Okay. So for example, x is positive of 10 raised power minus 20. So what does y become? Y tends to infinity. Y becomes 10 raised power 20, which is a very large number. Whereas on the other hand, x is tending to 0 but negative. Okay. So then y tends to minus infinity. So for example, if we take x as minus of 10 to the power minus 50, then y becomes minus of 10 raised power 50. So it tends to minus infinity as x tends to 0, but from the negative side. Okay. Similarly, as x tends to infinity, y tends to 0. Or as x tends to minus infinity, again y tends to 0. So the graph reflects this particular nature of the function. Just like this, we will show that it never touches this, but as x goes closer and closer to 0, but on the positive side, y goes closer and closer to infinity. Similarly, as x tends to infinity, y tends to 0. Okay, whereas, example here, as this kind of. So the again the negative part of the domain is like an inverted mirror image of this. Same kind of graph, but inverted mirror image. Okay, so again in the graph you can see that we cannot define the value of y when x is equal to 0, because just before x equal to 0, at some negative point which is very small, y is tending to minus infinity. And then as you cross 0 and go to a positive small point, it jumps from minus infinity to plus infinity. So that's why at the point 0, we cannot define what the value of x is. Sorry, what the value of y is when x is equal to 0. Because this thing just to the left of 0, it's tending to negative infinity. Just to the right of 0, it is tending to plus infinity. So exactly at 0, y becomes undefined. Okay. So, like this, we can go on and on about the properties of functions, because functions itself is like, a very, very extensive topic. I mean, polynomial functions alone, are such a rich and huge variety of functions. So if we include other things like trigonometric or hyperbolic relations and all this, then it becomes even much more wide. But here we will have to stop at a certain point and move on from just the general description of functions to the concept of rate of change of function, because that is the main point of interest for us, the rate of change of function. And that's where we will start with the first part of calculus, which is differential calculus. So rate of change. For a function y is equal to fx. Now, just like we talked about rate of change in context of speed last time, now we will talk about rate of change in context of a function, and we'll see that there are two types of rate of change. Okay. The first is called the average rate of change. Of y with respect to x. So again, just like average speed, this is defined for an interval. is defined for an interval of x. Okay, let's say x equal to x1 to x equal to x2. So the definition of average rate of change becomes, the symbol we use for it is delta y by x, delta y by delta x, which is the change in y upon the change in x. So it is y2 minus y1 upon x2 minus x1. So given a value of x1 and x2, how we correspondingly calculate y1 and y2? So here y1 is equal to f of x1 and y2 is equal to f of x2. So the definition of the average rate of change in terms of formula, it becomes f of x2 minus f of x1 upon x2 minus x1. So this formula gives us an exact method of calculating the average rate of change for any function from x equal to x1 to x2. This becomes, you can say, both the definition and the formula for it. So for example, let's say we have the function y is equal to x square minus 2x. Now I say calculate the average rate of change from x equal to 0 to 1 and x equal to 1 to 2. Just try this out, people. Note down this definition and try this question out. I'll put up the answer in just a moment. Just try it out and send me a text message. Yeah, Darsh, to answer your question, I will tell you that the difference between parabola and hyperbola in future. Okay, parabola is the graph of a quadratic function, whereas hyperbola is the graph of what we call hyperbolic type of functions. So an example of hyperbola is this one: y is equal to 1 by x. The graph of this one that we drew, the graph is what we call a rectangular hyperbola. Okay, it is part of a family of curves in coordinate geometry called hyperbola. And hyperbolic curves are defined by a certain relationship. Like a circle is defined as a certain relationship, that it's the locus of points which are equidistant from a particular point, which is called the center. Similarly, we have ellipse and hyperbola in coordinate geometry, which is defined in terms of the distances from two different points. Okay.
Yes, sir. So ellipse has like two focal points. So in
Yes.
hyperbola, so something similar like that.
Yes, hyperbola also has two focal points, but the hyperbola is a locus of point which has a common difference of distances from 2 points, whereas ellipse is the locus of a point which has a constant value sum of distances from 2 points.
Okay, sir. Got it.
So you will read about this in coordinate geometry in future also. Yeah, your answers are all correct. Vineet, Arya, Manav, Om. Okay, so just giving you the answers. I'll show you the method in just a moment. This one will have the average rate of change as -1. Is it? Okay. And this one will have +1. Yeah, so I'm sure all of you must have worked out this. So it's very simple. We have to just apply the formula over here. So for example, the A part, x equal to 0 to 1, we have to calculate delta y by delta x for the function y is equal to x square minus 2x. So we take x1 as 0. So y1, which is f of x1, becomes f of 0, which is 0 minus 0 or 0. Okay. And we take x2 as 1. So y2 becomes f of x2. That means the value of the function at x equal to 1, which as you can see is 1 minus 2 or minus 1. So now from this we can see delta y by delta x is f of x2 minus f of x1 upon x2 minus x1. So that we'll simply substitute as minus 1 minus 0 upon 1 minus 0. That becomes minus 1. So that's how this becomes. Similarly, in the second case, x equal to 1 to 2. So x1 is equal to 1. So y1 is this, okay. And x2 is equal to 2. So y2 is f of 2, which is 2 square minus 2 into 2. So that's 0. So these are the values. So now delta y by delta x. This now becomes 0 minus of minus 1 divided by 2 minus 1. So that becomes plus 1.
Sir,
Yes, any doubt, Vita?
how it came 2 square?
Because the function is x square minus 2x. No? So in the function, x square minus 2x. So if I want to find the value of the function at x equal to 2, I'll have to substitute x as 2. No?
Okay, sir.
What? Okay, so now that we've seen an example of average rate of change, let's understand the geometrical interpretation of average rate of change. So if we have represented our function geometrically through a graph, then with respect to that graph, when we want to interpret what is the average rate of change quantity between 2 points x1 and x2. So if let's say this curve is in general representing the function y is equal to fx, and let's say this point here is x1, and let's say this point here is x2. So we want to find average rate of change delta y by delta x for the interval x equal to x1 to x equal to x2. Okay. So graphically, if we look at it, this point here, let's say E, this is the point on the graph which has an x coordinate of x1. So its y coordinate is y1. Okay. And graphically, if you look at it, this point on the graph or on this curve, this point is, let's say, B. That is the point where the x coordinate is x1 and the corresponding y coordinate, or rather x coordinate is x2. and the y coordinate is y2, where y1 is equal to f of x1 and y2 is equal to f of x2. Okay. So now delta y by delta x is y2 minus y1 upon x2 minus x1. So we interpret what is y2 minus y1 in this graph and what is x2 minus x1. You'll see that this distance here is delta y. It's nothing but y2 minus y1. And you'll see that this distance here is delta x or x2 minus x1. Okay. So that means that if I were to join these two with a straight line, the points A and B, if I were to join them by a straight line, then the quantity delta y by delta x is nothing but the slope of the straight line. Okay. So hence, what we do is we give this a special name, this type of straight line. It is called the secant line. You might have heard the term before. So it is called a secant line joining the points A and B on the graph. And the slope of the secant line is nothing but the geometrical meaning of the term average rate of change. So this angle is theta. This angle is also theta. So such a straight line is called a secant line, which joins two distinct points on the graph, in this case A and B. Okay. So the interpretation of this is that it becomes the slope of the secant line tan theta. So secant line is a straight line joining the two distinct points, in this case A and B, on the graph of y is equal to fx. So this is the geometrical interpretation, that average rate of change is slope of the secant line.
Sir, but
Yes.
if this function curve continues to rise, then the secant line may cut more than 2 points on the line. So
Yeah, it can cut more than 2 points. But the thing is that when we are drawing the secant line, now which 2 points we have to select? The 2 points corresponding to the interval for which we are calculating rate of change. So we want to calculate the rate of change from x equal to x1 to x2. So the secant line that we are drawing should be joining the points x1 y1 and x2 y2. Now that might cut at other points also, it doesn't matter. But what is the definition of that line? It is the line joining these 2 points on the curve of the function y is equal to fx. Understood the point, no?
okay, sir, got it.
Okay, so as an example, let's go back to the question we had just done. We had the function y is equal to x square minus 2x, and we wanted to find out delta y by delta x from x equal to 0 to 1. Okay. And second part 1 to 2. So first of all, let's see how we draw the graph of the function y is equal to x square minus 2x. Okay. Now see, this is a quadratic function. Okay. So it will have a parabolic graph. So in general, any quadratic function like this, it has a parabolic graph. Okay? But depending on whether E is positive or E is negative, okay, the parabola has a shape such that it is either opening upwards or opening downwards. Okay. The most basic example of this you can see is that the function y is equal to x square. It looks like this. It's a parabola opening upwards. But if we take the function y is equal to minus of x square, so the value of E is -1. Here the value of A is +1. And that one looks like this. Okay. Now similarly, if we take an example of y is equal to 1 minus x square. Now you can see if you compare it with this, you can see that it is basically y is equal to minus x square, and to that I have added 1. So this graph just has to go up. So from this graph, we have to generate this by just lifting this up by 1 unit. So this goes here. This point, which is called the vertex of the parabola, it just goes to 0, 1 instead of being at the origin. And correspondingly, all the values change. Okay. So without getting just a moment, people. Okay, I'll reshare the file. Yeah, so in general, if I have a quadratic expression like this, depending on whether the coefficient of x square, which is A, is positive or negative, the parabola will be pointing up or it will be pointing down. So in this particular case, y is equal to x square minus 2x. You can see that the coefficient of x square is 1. So it's a positive quantity. That's the first thing I can see. Okay. Now the second thing I can see is that this is very easy to factorize. I can factorize it and write it like this. So we can see that y is equal to 0 at x equal to 0 and x equal to 1. Oh, sorry, x equal to 2. So these are what we call the roots. They are the values of x for which y becomes 0. So they are the roots. In terms of graph, what it will mean, they are the points at which the parabola will intersect the x-axis. The value of y should be 0. So that means the parabola should go through the point 0, 0. Okay. And similarly, when I substitute the value of x as 2, the value of y should again be 0. So it should be going through this point, which is 0, 2. So a parabola pointing upwards like this, which goes through these 2 points, how the shape of the graph will look something like this. And in fact, this point in between will be 1, where if you check the value of the function, we had seen it was -1. So this point was 1, -1. So now you can indeed see the graphical interpretation. We want to find out delta y by delta x for x equal to 0 to 1. So what we'll have to do is we'll have to draw a secant line joining these 2 points. So that secant line will now look like this. So you can see that it has a negative slope. This particular secant line has a slope of -1. So that is why this average rate of change was -1. But on the other hand, if we are calculating the rate of change for x equal to 1 to 2, so that means we are taking this point and this point, and we are joining them by a secant line. So that secant line will now look like this. It has, as you can see, a positive slope. So this becomes plus 4. Because this was our graph of y is equal to x square minus 2x. Or that is the same thing as x into x minus 2. Okay. So this is an example of the application of that concept, that the geometrical interpretation, that average rate of change between 2 points is equal to the slope of the secant line joining the 2 points on the graph. Right. So as you can see, this is a comparatively easy definition because we have a direct formula that this average rate of change is y2 minus y1 upon x2 minus x1. Okay. Now let's move on to the second type of rate of change, where actually we will get into the introduction of differential calculus. Instantaneous rate of change. Okay. Of y with respect to x for a function y is equal to fx. Now today we will see the proper calculus definition of this. So according to the proper calculus definition, this quantity instantaneous rate of change, it is given a special symbol. Okay. It is given the symbol dy by dx instead of delta y by delta x. It's given a special symbol. So this is the symbol for instantaneous rate of change. Okay, of y with respect to x. So instantaneous rate of change means rate of change at a particular point, not for an interval. At a particular point x equal to x less, not for an interval x1 to x2. So how we define this algebraically? We define this as the value of delta y by delta x only, but under a special condition, which you might have heard is called a limit. And that limit is that delta x is tending to 0. So this is the definition of instantaneous rate of change in terms of calculus. This is the differential calculus definition. So the meaning of this term here, limit delta x tends to 0. What this means that delta x is what we call an infinitesimal interval. Or another word for it is, it's a differential change. In x. So that basically means that it's extremely small. such that it tends to 0. Okay. So practically what we mean is that think of a very small number like 10 raised power minus 50 is unimaginably small. Okay. And then make it even smaller. Take 1/1,000,000th of it or 1/1000,000th of it and take something even smaller than that and go on doing that till you reach a number that is so small that you cannot imagine how small that is. It's so small that it's tending to 0. Okay. So that is the meaning of this term, that delta x is tending to 0. So further, we see here for y is equal to fx, this function, dy by dx will become what we call limit delta x tending to 0 of delta y by delta x. So this will further be defined as, so in this case, what we are doing is delta y by delta x was y2 minus y1 upon x2 minus x1, where y1 was f of x1 and y2 was f of x2. Now, when we are taking this situation, what we are doing is that we are taking x1 as x, x2 as x plus delta x, but under that limit, that delta x tends to 0. So correspondingly, y1 becomes f of x, but y2 becomes f of x plus delta x. But again, under that limit, that delta x is extremely small, so it's tending to 0. So further, this becomes limit delta x tending to 0, f of x plus delta x minus f of x divided by delta x. So this becomes the algebraic definition of instantaneous rate of change. So from this, we can see that for the given function, algebraically, how do we define the quantity instantaneous rate of change? It is the calculation of this limit, that delta x tending to 0, the change in the y coordinate at a point fx divided by the change in x coordinate, but under the condition that the change in x coordinate is extremely small, it is tending to 0. Okay. So this is the meaning of dy by dx algebraically speaking. So I'll just minimize this for a couple of minutes. Okay. Just go through this part, study it, and make sure the meaning of each term is clear.
Sir, how to calculate delta x in instantaneous?
So that is the thing. Now we have to substitute for a given function. Na? We have to substitute this limit that we have put in the box below. F of x plus delta x minus fx divided by delta x. And on substituting that limit, we have to make delta x tending to 0 and calculate how much it is. So for example, we will see next that if we take the function as x square, then the value of dy by dx or instantaneous rate of change comes out to be 2x. If we take the value of the function as x cube, it comes out to be 3x squared, and so on and so forth. But that comes by applying the definition of this limit. So it's a further process in algebra. You're understanding my point? Algebraically, we have to calculate what this value on the right hand side is. F of x plus delta x minus fx divided by delta x under the condition that delta x is tending to 0. So that algebra that we develop now for calculating this thing, that only is called differential calculus. That is a process of differential calculus.
Okay.
Okay. Okay, so just make a quick note of this. Okay. Then we will see with some examples next how we calculate this. Okay, so this is the algebraic definition. Now let us see the geometrical interpretation of that. And hopefully that will make us understand it a little bit better. So let us say this is the graph for a particular function. Y is equal to fx. And at a particular value of x, I want to find the instantaneous rate of change. Okay. At some value of x equal to x over here. So geometrically, what I have to do is literally this, that I have to. So first of all, you can see that this point, it has some particular y coordinate, and x and y satisfy this relation that y is equal to fx. Now I have to zoom in as much as I can. So I'll try to magnify this as much as I can. Okay. So I have to zoom into this and I have to take a point which is very, very close to this, so that the interval between these 2 points is almost tending to 0. So I'll have to take a point like this now, which is extremely close, so close that when I zoom out of the diagram, these 2 points are almost going to merge into a common point. So this point is such
Tangent, right?
so it will become a tangent line when I join those 2 points. So these 2 points are so close that this interval between them is what we call that differential or infinitesimal change in x. So this is our dx, which is nothing but a delta x under the limit that delta x is tending to 0. So correspondingly, the change in the y coordinate will also be very small. So that will be our differential change in y, or our infinitesimal value of delta y. And their ratio will be nothing but the instantaneous rate of change. So now if I try to join these two points, okay, it's a bit of a hazardous job, but what I'll do is make it as fine as possible. Yeah. So if I join these 2 points, the line. So hopefully I should get something that looks like this. So when I zoom out of this diagram, you will see that this line looks like it almost touches the graph at one place. It intersects like 2 points, which are like consecutive points on the graph. Earlier we were seeing that the graph is a continuation of points one after the other, which all satisfy the equation of the straight line, the equation of the function. So now this line which I've drawn, it is nothing but 2 consecutive points on the graph at x equal to x and x plus dx. And we are continuing that into a straight line. So that kind of line is called a tangent line. So the interpretation of dy by dx now becomes, it is the slope of the tangent at x equal to x. So instantaneous rate of change equals to slope of tangent. So a tangent line joining a particular point with let's say a point at x equal to x with another consecutive point x equal to x plus dx on the graph. So this dx is basically like a delta x tends to 0. Okay. So the 2 points almost merge. So that is how, hypothetically, or that's how in terms of our imagination, a tangent line should be drawn and the slope of that tangent should be equal to the instantaneous rate of change. So as you can see here that this is still an abstract concept. Okay, still this is an idea. It's not a practical method yet that given a particular graph, we'll be actually able to draw the tangent line. Of course, if we have plotted the graph using a computer program, then we would have a series of points one after the other, such that the distance between those points is extremely small. So we could use that program to generate the tangent line and find the slope, but still it's going to be a complicated process. It's not going to be a simple process. So that is where now the principle of differentiation, or you can say the differentiation is like a mathematical tool. It's like a machinery. So that mathematical tool is going to give us a very direct method of being able to calculate the slope of the tangent. Okay, so differential calculus is all about this thing only, that given a function, how can we very conveniently, through a set of very straightforward formulae and principles and tricks, how we can find out the slope of the tangent at a given point. Okay. So hope this geometrical interpretation as an idea is clear to all of you. So next we will see how differentiation itself works. Okay. So let us understand the process of differentiation with an example. Differentiation. What is differentiation? It is an operation it is an operation that comes through application of the subject which we call differential calculus. Now this differentiation operation results in the calculation of instantaneous rate of change. So the differentiation operator is given this symbol. Okay, so this is the symbol for differentiation with respect to x. So that's how we read this. Okay. So when this operator is applied on a function, it gives us rate of change, instantaneous rate of change of fx with respect to x. We can also visually think of this as an operator which does this operation. So when we input the quantity, when we input a function y is equal to fx, the output that this gives us is the instantaneous rate of change of that function. So it is differentiation of that function where the output is the instantaneous rate of change when the quantity we import is a function. Okay. So this is the terminology of differentiation. Okay. So for example, if we have a function of time like this, then we can differentiate that operator, I mean that function, with respect to time, and this will give me rate of change, instantaneous rate of change of s with respect to t. Okay, but in the standard notation we use y and x as the symbols. So y is the dependent variable, which is a function of the independent variable x, and if we operate the differential operator or the differentiation operator on that function, it will give me the instantaneous rate of change. It will give me a formula for the instantaneous rate of change. Okay, now how exactly this calculates the instantaneous rate of change? It calculates from that algebraic definition. Okay, so how does differentiation of a function actually work? It comes from the algebraic definition of instantaneous rate of change, that this one. Okay, so by applying this definition only, we get all the formulae for the differentiation operator. Okay. So formulae of differentiation. So for example, one basic formula is that differentiation of x to the power n, where n is any real number. This is given by nx to the power n minus 1. So I'll show you some examples in a moment that how this formula actually comes. This formula comes from an application of this kind of principle. Okay. So for example, if y is equal to x cube, then differentiation of y with respect to x, or rate of change of y with respect to x, will become this. So that will become 3 into x to the power 3 minus 1. So that will become 3x squared. So just make a quick summarized note of this.
So how does that 3x come there?
How does the 3x square come now? So as of now, see, we have just applied the formula. I'll explain how the formula is actually derived from this also. But we've just applied this formula. Differentiation of x to the power n is given by the formula n into x to the power n minus 1. So यहाँ पे what is the power of x? It's 3. So just substitute n with 3. So it should come out to this according to the formula. Okay, this you understood now how the formula is being applied here. Okay. Of course, where the formula has come from, that is a different matter, and I'm going to show you that. Okay. So for example, just use this before we get into the derivation. Okay. let's just see the use of this formula for some more examples. Y is equal to root x. Find out what this should be. Y is equal to 1 by x. Find out what this should be. Okay. Yes, very good. That's correct. Parv, Muskan, Parth. Okay, so let's see these ones. For this one, this is differentiation of root x, which we can write as differentiation of x to the power half. So that will become half into x to the power half minus 1, or x to the power minus half divided by 2. So we can also write this as 1 by 2 root x. Okay. So this will be for this one. Okay. Similarly, for this one, this is differentiation of 1 by x. So when we express this as a power of x, it's x to the power minus 1. So it will become n x to the power n minus 1. So that is minus x to the power minus 2. Or we can say that this is minus 1 by x squared. So that's, for example, how we can use this direct formula to calculate the differentiation of any power of x, like this. Okay, including, we can also see that if y is equal to x, the rate of change will become 1. You can see now, it will become become 1. Now this totally makes sense, because if you think about it, this is a straight line of slope unity. Na? So instantaneous rate of change should be equal to average rate of change, should be equal to that slope, which is 1. So at least in the case of y is equal to x, you can see how the logic of this formula. Right, this is clear now, all these examples?
Yes, sir.
Okay. Now let's see how we can actually do it by the algebraic definition. So let's take one of these examples. Let's take the example of y is equal to x cube. Now we want to find out dy by dx, but by the definition, okay, the algebraic definition, not by the direct formula. So by the algebraic definition, for y is equal to fx, okay, the instantaneous rate of change is defined by the calculation of this limit. I'll use the symbol LIM as a short form for limit. This is what we have to do. Okay. So for this function now, we have to apply this now. Okay. So y is equal to fx equal to x cube. So for this, dy by dx will become limit delta x tending to 0. Now just replace this thing with this function. So it will become x plus delta x whole cube minus fx will become x's cube divided by delta x. Okay. So far this is clear, this step?
Yes, sir.
Okay. Now see, if I put directly delta x tending to 0, I'll get x cube minus x cube divided by 0. So I'll get 0 by 0. So that's not solvable. That's not allowed in maths. So I have to algebraically solve this further till I can put delta x equal to 0. So to solve this further, one of the tools I have is I have this formula that a plus b whole cube I know is this. So I make use of this formula and see if it's going to help me. So before substituting the limit, I have to solve it such that I can substitute the limit and get some finite answer. It should not give me something undefined. So x cube plus 3x squared delta x plus delta x, sorry, plus 3x into delta x squared, and then finally delta x cube. Okay, this is the expansion of this term. And of course, I have minus x cube. So I can get rid of the x cube. So this will further give me 3x squared delta x plus 3x delta x square plus delta x cube. So it is somewhat simplified, but still you can see that if I substitute delta x as 0, I'm still getting 0 by 0 form. So now the next step is very critical here. Okay, so pay attention. So the next step, what we'll do is we will take delta x common in the numerator. So once we take delta x common, we get 3x square plus 3x delta x plus delta x square divided by delta x. Now see, this is the most critical step I'm coming to. What we know about delta x tends to 0, but delta x is not equal to 0. Okay, there's a difference between the two. We are saying that something is so small that its value is almost equal to 0, but that doesn't mean that we are saying it's equal to 0. So as long as delta x is not equal to 0, we can say that delta x by delta x is unity. If it were equal to 0, we could not say that, because then it would be 0 by 0, which is undefined. But here delta x is tending to 0. So that means it's definitely not equal to 0. Okay, so that means we can do this cancellation. Okay, and we are now left with the solution, with the calculation of this limit. Three x square plus 3x into delta x plus delta x square. Now you can say that, okay, if delta x is tending to 0, then in this bracket, the second and third term are tending to 0. This whole term is also tending to 0. This whole term is also tending to 0. Like imagine, delta x is something like 10 raised by minus 200. Okay, so actually delta x is even smaller than that when its limit is tending to 0. But you can imagine how small this number is. So practically this whole thing and this whole third term, they are tending to 0. So what is the value? It is 3x square. So you can see the calculation of this limit algebraically results in this. So this is the proof that differentiation of the function x cube is 3x square. So in the proof of this, what we've actually made use of is what we call binomial theorem, the application of a plus b to the power n. N in this case is equal to 3. Similarly, it would be very easy for you to prove that the differentiation of x square is 2x. But to prove that the differentiation of x to the power minus 1 is minus 1 by x square is a little bit more complicated. Okay, because it involves binomial theorem application for the power being minus 1 instead of the power being 2 or 3, which is something that we are familiar with. But similar method exists for each and every formula of differentiation that we are going to study. Okay, so I hope this process is clear. Okay, in maths, this process is called differentiation by first principle. Okay, when you study advanced calculus in maths class 12, you will see that this process is called differentiation by first principle. And the proof of these kind of formulae are actually part of your math syllabus. But for us here in basic calculus, the proof and the derivation is not so important. It's important for our understanding. But for our application, we just need to know what the formula is and understand how we apply the formula. Because ultimately, we are going to apply differentiation to physics problems, okay, where the differentiation step is going to be one part of the problem. The main thing is solving the physics of it. Okay, so make sure the logic of each and every step here is clear to you. Ask me any doubt if you have a question.
Sir, so the derivative of x cube is not exactly 3x square. No, it's 3x square plus some very small amount, right?
So now see, that is the point of where it becomes like quite an abstract subject. Very small amount का मतलब यहाँ पे क्या है? I'm applying the limit that delta x is tending to 0, no?
Yeah.
So again, you have to imagine that point is almost merging with the first point, no?
Yeah.
So it's becoming 3x square only, no?
Acha. So when we cancel delta x by delta x, at that
Yes.
time we like do not take it as 0, but then
For all practical purposes, it's 0. You understand? No?
okay.
It's not exactly equal to 0, but it's almost equal to 0. It's as close to 0 as we can imagine. So that means in the limit that it's tending to 0, we can say that this term is exactly equal to 3x square.
Okay.
Okay, so that is where it's a little bit abstract as an idea. But if you revise the concept again and again and think about this correlated with the graph, it will start making sense to you. Okay. Also, like let's see how we can interpret this geometrically. So for example, what information this tells us, that if y is equal to x cube, it's telling us that dy by dx is equal to 3x square. So what is the meaning of this geometry? Any x equal to x is given by that slope should be equal to 3x square. So let's just recall the graph of y is equal to x cube. Okay. And here, just for simplicity, I'll take it only on the positive side. But actually, we can take it on both sides. It doesn't matter. So for example, on the positive side, the graph of y is equal to x cube looks something like this. Now this means that if, for example, at the point x equal to 1, I choose to draw a tangent. So what should be the slope of that tangent now? It should be 3. So this should have a slope equal to 3. Because at x equal to 1, so we'll have a value of 3. So this is telling me that the slope of the tangent at the specific point x equal to 1, that is equal to 3. Okay. But now compare that with the slope at another point. Like suppose this is a point x equal to 2. So the tangent drawn at this point will have a much steeper slope, you can see. So its slope will become how much? Slope will become 12. Okay. So this is the interpretation of this graphically now. What it means that the instantaneous rate of change is 3x square. It means that the general value of slope of tangent is equal to 3x square. So at a particular point x equal to 1, the slope is this much. At a particular point x equal to 2, the slope is that much. And so on and so forth. Okay. Now it also shows you the symmetry of this graph, because if you were to compare the point x equal to 1 with the point x equal to -1, you would see what we are talking about. That graph here is like this. You can see that when I draw the tangent at a point like this, I'm getting a line like this. When I draw the tangent at a point like this, I should get exactly a symmetrical line. These two tangents should be parallel to each other. So if this point is -1 and this point is +1, then this also has a slope of +3. This one also has a slope of +3. So that is the interesting property that this x cube graph is having. It has an exactly symmetrical shape. So that's the property that you can see through the instantaneous rate of change concept also. All right, so hope this is clear. Now, just to wind up today's session, we will see a couple of more important things about instantaneous rate of change. So as part of the formulae, we'll understand that instantaneous rate of change of any constant is equal to 0. And this is very easy to visualize, because if you have a constant function, what does the graph of this function look like? It looks like a horizontal straight line. So the slope of the tangent at any point, whether it is tangent or secant line, whatever we take, is 0. So dy by dx will be equal to delta y by delta x, will be equal to 0 for y is equal to c. Similarly, if we have a linear function, y is equal to mx plus c. So again, we can see that this graph of the linear function is a straight line, which itself has a slope. Sorry, need not pass through the origin. So let's take a general straight line. So it itself has a slope equal to m. So that means whether we draw tangent at a point or we draw a secant line, both will have a slope of m. So that means that instantaneous rate of change of a linear function mx plus c is a constant. Okay. So these are two formulae apart from the main formula that we saw today, that differentiation of x to the power n is nx to the power n minus 1.
Sir,
Yes.
what determines that the slope of a line, a
Ah.
tangent, is positive or negative?
The value of m determines beta. So for example, if I have a line y is equal to 2x plus 3, this will have a slope which is positive. Okay. But if I have a line which is 3 minus 2x, this will have a slope which is negative.
Okay, okay.
Yeah. So like for example, when we write v is equal to some u minus at, that velocity with respect to time is having a negative slope because it's decelerated. Whereas if it is u plus at, it's having a positive slope because it's accelerated uniformly.
Okay, thank you, sir.
Okay.
For
Yeah.
two tangents to be parallel, the y should be equal to x cube, right?
No, that is the property of that one. It need not be only in that case. Okay. It can be some other function also. You're understanding my point, Beta?
So for
example, you have the function y is equal to x to the power 5. इसके लिए भी symmetric होगा, because dy by dx will be 5x to the power 4, no? So you can see slope of the tangent at x equal to 1 will be the same as at x equal to minus 1, or at x equal to 2 will be the same as minus 2. Agree?
Yes, sir.
So any even power of x will give you that kind of symmetry, that when we draw the slope of the tangent at some positive value of x and at the same value but on the negative side, the slopes will be the same. Okay. So that's just a matter of symmetry. Okay. All right. So before we conclude, now one last important thing, which is two properties of differentiation. Okay. So the differentiation of a constant into a function we can take the constant outside and just differentiate the function. Okay. So for example, if y is equal to 5x square, now I want to find out dy by dx. So that is differentiation of 5x square. So the first step here is I'll take the 5 outside. And then the next step is I'll apply this formula. So this becomes 5 into 2x to the power 1. So finally the answer becomes 10x. So the differentiation of x square is 2x. So the differentiation of 5 times x square becomes 5 times 2x, which is 10x. Okay. So this is this formula. All right. So I think we've exceeded the time quite a bit, so we'll conclude here today. Okay. But there are a couple of more properties which we'll be looking at in the next lecture. You can also start reviewing them from your module. So the chapter of differentiation or differential calculus, I think it starts around page 25 of your module 1 of physics. Okay, so you can start going through it, and I'll be giving a worksheet also. Also, I forgot to mention, hope you have worked out the questions in worksheet 1, which I gave you last week.
Yes,
I've also
sir.
sent you some hints and solutions. No? So you will see that after today's lecture, you can also solve some of those problems using differentiation. Okay, but the questions were designed in such a way that you did not actually need to use differentiation. You could have solved them just by using simple concept of ratio and proportion and average rate of change, as I have done in the solutions. So study those solutions if required carefully. If there are any doubts, you can send them to me. In the next lecture, I will discuss any doubts in worksheet 1 as well as worksheet 2, which I'll be sending you. Okay, I'll be keeping some time aside for discussing of the doubts also. Also, if you have joined the Discord platform, then you can send the doubts on that also, and it's a very convenient platform to all the information, including the links for the videos and the notes and all are all organized in one place. There's a common page for physics and physics doubts, similarly for chemistry and chemistry doubts and all that. So if you haven't joined the Discord platform, you can please do that also. I think Tausif sir has sent you the link on your WhatsApp group for Blue House. Okay. So anyhow, that's it for today's session, people. Hope you have enjoyed learning today, and thanks for attending. Okay, see you next time.
So,
Thank you, sir.
Thank you, sir. Bye, sir.
Excuse me, sir.
Yeah, beta.
Sir,
Bye, sir. Thank you, sir.
Link
Okay, bye.
Tausif sir has sent, it has expired. So I am
Sorry,
not
which?
able. Sir, the
Actually, the link has expired. Yeah. Okay.
Yes, sir.
I'll send it again, beta. We'll send it.
Okay, thank you, sir.
So just be alert on the WhatsApp group. Now, sometime today the link will come again. So that time join it. No?
Okay, sir.
Okay. Yeah, beta.
sir, actually, I'm having doubt in the worksheet 1. This second.
Okay. So in the second question, you just use simple concept of rate of change. Like, the tank is empty initially and the inlet is putting water into it at a certain rate, so many cubic centimeters per second, right? So you use unitary method that per second, if the amount of water coming up is 4 cubic centimeters, then after n seconds, it will become how much? It will become 4n. Okay, and then use geometry that the volume of liquid in the container is equal to area of the base multiplied by height. Okay, so if you have a formula for volume at time t, from that formula you will have height at the time t, and from that you can understand how height is changing with respect to time.
Okay, sir.
So
And sir,
just
can
try.
we
Yeah.
have a graph for logarithmic function?
Yes, there is a graph for logarithmic function, both exponential and logarithmic function. You will find the graph in the standard text also, but I will be discussing it when we come to differentiation of those functions. Okay.
Okay, sir.
Okay.
Thank you, sir. Bye, sir.
Bye, sir.
Oh,
Thank you, sir.
okay. Thanks, people. Okay. Bye.